This is an empty Coke can, and this is a rubber rod. Today we're going to use these two objects to take a look at electric charge and something called Coulomb's law. See, when I hold the rod close to the can is attracted to the rod. There's a force between them. There are no tricks here. There's no strings or magnets, and there's not a motor hidden in the can. The can moves because of charge and an invisible thing we call the electric force, which exists between these two objects. So to better understand the electric force, let's set the can and rod aside and instead take a look at another invisible force we're already used to: gravity. We've seen in the past that when we're dealing with any two masses, say the Earth and the Moon, there's a gravitational force between them. And that force by gravity acts equally on both masses to pull them towards each other. Now, much in the same way that gravity can produce a force between two masses, the electric force acts between two charges. See, anytime there are two charged particles near each other, there is a force between them due to something we call the electric force. And that electric force acts between these two charges even though they're not actually touching each other, much like gravity acts between these two masses even though they're not actually touching one another. Now, the similarities between the electric force and our force by gravity don't just end at our cute little pictures here. They extend also into the math that drives what's going on with these two situations. So to understand mathematically what's happening with the electric force, first let's take a look at our equation for the force by gravity. See, the force by gravity between two masses is given by Newton's law of universal gravitation, which he came up with in 1687. And that law says that the force by gravity between two objects is given by the gravitational constant multiplied by the product of the two masses over the distance between them squared, where the gravitational constant is this value, 6.67 times 10 to the minus 11th. So in looking at this equation, we see that the force by gravity increases as either the two masses increase in value or the distance between the two masses decreases. And in taking a look at the electric force, we see an almost identical equation. This equation, which was developed by Charles Coulomb in the 1780s, relates the electric force between two charges to the quantity of charge which each charge has to the distance between each charge. Where the distance between each charge is what we call the radius, even though it's actually the center to center distance of each charge. And much like with gravity, where we have a constant which relates just how strong this force by gravity is to the actual masses and their distance, when dealing with the electric force, we have a constant called Coulomb's constant, which relates the electric force to the quantity of charge and the distance between those two charges. Now, in calculating the force by gravity between two masses, we need to know their masses in kilograms. When looking at the electric force between two charges, we need to take a look at the charge of those two particles measured in coulombs, which were named after Charles Coulomb. And 1 coulomb of charge is equal to the charge possessed by 6.24 times 10 to the 18th electrons, which sounds like a lot of electrons, but in reality, it's not that many. Now, there's one major difference between the electric force and the force by gravity. See, the force by gravity always tries to pull two masses together, but the electric force sometimes tries to pull charges together and sometimes tries to push them apart. And we find the electric charge pulls two charges together when those charges are of the opposite sign. And it tries to push those two charges apart when they're of the same sign. So let's go back to this Coke can to see how and why this can is being pulled around by this rod. Now you already know that all matter is made up of atoms, which consist of protons, neutrons, and electrons. You realize those protons carry a positive charge, and electrons are in fact a negative charge. So when we look at the rod, it has both positive and negative charges. And the same thing goes for the can. It's made up of positive and negative charges. Now the charges in the can are balanced. That is to say there's as many protons as there are electrons. But the rod has a buildup of electrons on it. So we could say it has a net negative charge. But these charges over here on the rod are stuck in place because the rod is what we call an insulator, and it does not allow charges to move around. But the negative charges on this rod are not only pushing on the other charges within the rod, they're also pushing on the charges over here in our can. But this can, unlike the rod, is what we call a conductor. And that means it allows the negative charge, or the electrons, to freely move around inside this material, or the aluminum which the can is made from. So when we place this rod close to the can, there's a repellent force between the negative charges of the rod and the electrons in the can, which pushes the electrons to this side of the can. Now in reality, not all of the electrons move. It's only a few of the valence electrons move. But in causing some of the charge to shift over here, what happens is this can becomes charged through a process we call induction. And this leaves us with the left side of the can having a net negative charge, and the right side of the can having a positive charge. So think of our negatively charged rod as pulling the positively charged side of the can toward the rod, and pushing the negatively charged side of the can away from the rod. Now, because the electric force, according to Coulomb's law, gets smaller the farther away two objects are, the force between the positively charged side of the can and the rod pulling the can towards the rod is greater in magnitude than the force repelling the far side of the can away from our negatively charged rod. And this results in a net force on the can, causing the can to accelerate towards the rod. So that is why the can moves when the rod gets near it. And that's all for now.